All right, so what we're going to be doing now is discussing a little bit about how someone would know that VO2 max was actually truly the VO2 max and that the person maybe didn't stop a little bit too soon. We're going to be looking for a couple different things and we're going to walk through each one of these a little bit. First one here, this RER greater than 1.1, this is a respiratory exchange ratio. We'll talk about what that is. We're also going to be looking at these kind of comparing to a chart what your age predicted max heart rate would be, and ideally you should be above that if this is truly going to be a valid VO2 max test. And finally, you're going to be looking for a plateau in the VO2 even though intensity of exercises is increasing. Don't always see this, but if you do, it's a good indicator that this was a valid test. So these are kind of these normal values of what would be a VO2 max for people of different ages, what would be kind of an average one to a very high one. Personally, I'm in the 40 to 49 age range. Mine is around 52 to 55, depending on my training. So I would be kind of right here. For a lot of folks, I'm usually going to be in this, for college age, somewhere in, for males, this range usually, females, right down here. So one of the things that we're looking for on these tests, and this is also kind of a neat one because when we talk about training and types of training to do in terms of longer endurance, shorter endurance, and other stuff like that, one of the things we talk about, and we talked about it already, was with those bioenergetics, the idea of using carbs preferentially versus fats. Respiratory exchange ratio is actually looking at what you're using as a energy source. So this is actually looking at, are we using carbs mainly or are we using more fats? And this can allow us to kind of determine if your training is possibly improved. If this number goes up, it means you can burn fats at higher and higher intensities. The other thing we're looking for when it comes to VO2 max is we want this number to be on the very high end of carbs, because we know if we're doing something at our max oxygen consumption, we should be using carbohydrates 100% and not any fatty acids. So again, looking at this stuff here, and we'll talk about how this works. So respiratory exchange ratio, very simply, is just kind of how much carbon dioxide are we generating for how much oxygen we're consuming. And again, because when we break down these particular products, carbohydrates do have oxygen within it. We can use some of that oxygen as part of the oxygen being consumed, versus with fats, there is no oxygen in them. If you're using those ones, it's going to require a little bit more oxygen in order to break those down. So at rest, generally, your respiratory exchange ratio is about 0.75. What this is really saying is at rest, generally you're burning about 85 to 90% fat and about 15% carbohydrates. As you increase intensity, and to do the numbers on this one, and we'll see it in just a minute here too, but 0.7 is 100% fat. 1 is 100% carbohydrate. So what we're looking at here is as you start increasing intensity, this 0.75 number should start becoming 0.8, 0.85 as we kind of go here. This idea is a lot of times why they think if you exercise at lower intensities, you're going to burn more fat. In reality, it just kind of comes down to calories in and calories out. If you are getting rid of more calories than you are consuming, that is going to lead to weight loss over time. There's things that makes the body try to hold on to them more and other things like that. But again, the simple thing is if more calories are being consumed or burned than we are consuming, then you will lose weight. So again, this is looking at that carbon dioxide production versus oxygen consumption. Again, this ratio, the higher the ratio, the closer we are to burning 100% carbohydrates. And this just shows you the idea here of you're taking a carbohydrate here with oxygen. And this shows you what it will break down to, that if we do the carbon dioxide that's generated versus the oxygen that we consume to do it, the ratio is 0.7. That is saying 100% fat. Sorry, this was a fat, not a carbohydrate. If we take glucose, for example, 6 O2s breaks down to this. We're consuming 6 oxygen molecules, generating 6 carbon dioxide molecules. That's a 1-to-1 ratio. What this is indicating is that you were burning 100% carbs at this point. And you can kind of see here as you work your way along this respiratory exchange ratio chart that at 0.7 it is 100% fat, at 1 it is 100% carbohydrate, and through the different parts of it along there, we can see that there's going to be different ratios as you work your way through. What we're kind of looking for, and when we're trying to get this respiratory exchange ratio above 1, that means you're starting to go above that aerobic threshold, and you're going to start generating carbon dioxide anaerobically. So when the anaerobic threshold is crossed, we can only do this for a little bit of time. We're going to generate a lot of lactate and therefore a lot more CO2 as a byproduct of making these more acid-based substances. And this will actually bring that respiratory exchange ratio above 1. You're starting to get non-metabolic carbon dioxide being released because your blood is getting more acidic. And this is just kind of showing these ideas with ventilatory thresholds. So this first one here is when you start generating lactate, you'll start being able to where you can't talk as easily. You'll start generating some lactate. The ventilatory, sorry, not the easiest one for me to say. Second threshold here is when we start getting that lactate far above there. And what that means is we're actually at that point starting to breathe to get rid of excess CO2. Our breathing rate goes to that, getting rid of that excess CO2 and not based on the amount of oxygen we're consuming at all. At that intensity, you really are just throwing out a sentence or so. This first one here, you're working harder, but you could still say a sentence or so. A lot of times people use these as kind of this idea about where they should be. Generally, when it comes down to it, they a lot of times talk about an 80-20 type of breakdown here. 80% of your training, if you're going to improve aerobically, should be below that VT1, and 20% should be above that VT2. Generally, you don't want to work in between them because you're not really preferentially getting either kind of system. You're not really getting into burning fats particularly well, and if you get above that one, you're working hard enough that if you're in between them, you're not targeting anything particularly well. And again, like it says there, sometimes VT1 for somebody who's just starting out, it's just a matter of getting out there at all. And sometimes that will be a little bit too high of intensity to begin with. The other thing we see with a lot of the stuff here is a lot of times we're going to consume oxygen at much higher levels after exercise than we did pre-exercise. So this idea that we talked about in A&P2 of an oxygen deficit is definitely something we also look at when we start talking about endurance exercise and kind of what's going on here. Oxygen deficit is just how much oxygen you consume during exercise, that once you get aerobic metabolism, if you could have did aerobic metabolism immediately, what was the oxygen we consumed that was not aerobic to get there? So things like this means is if you generate any lactate, if you get rid of any stores of ATP, creatine phosphate, all these things are going to require you to bring in more oxygen to put these back to normal after the fact. So again, we can pay attention to these as well. And again, we want to make sure if we're doing a valid test that we are getting definitely above there, and we should have a big oxygen deficit at the end of this test. So we're trying to put everything back here. So main thing is quickly we are going to put some stuff back right away. So of that exercise, that post-exercise oxygen consumption, very quickly we're going to restore the creatine phosphate system. Within about 3 minutes, it's fully back. It's going to be a little bit slower to clear the lactic acid. So like it says there, 70% of that is going to get oxidized. We're going to do some of it, conversion back to glucose, some of it to protein. And this stuff is going to take a little bit more time, up to an hour total to get through all this stuff.